Okay, cool. Recorded and summarized. That's what we want. So here's an example where we have been working with, as I said, Eleni Koronaki, who's now at LIST. She was a Marie Curie fellow in my team, and she worked a lot with a company called Surrogate in Luxembourg, which is one of the leaders in a process which is called chemical vapor deposition. So this is an example of what you can do with data-driven models and how you can decide what experiments to do, then use large language models to categorize certain experiments and to help engineers come up with better ways to design what they are working on, in that case, thin coatings. So what is the situation here? We are in a situation where we have a chemical engineering reactor. So chemical vapor deposition is a process which you can summarize in the following way. What you do is very simple to understand. You will put some chemical species in what is called a chemical reactor. Chemical reactor is a place where you have chemical gases, let's say, that are blown into a certain volume. In that case, it looks like a cylinder. It's building up and down here on the screen. And what you do is you blow these chemicals in, let's say from the bottom, and at a certain pressure, certain velocity, and certain concentration of chemicals inside this reactor. Why would you like even to do this? Because in this reactor are little so-called inserts. So these inserts are these little things here. And in the case we're interested in, these little objects are tools which are made by the company. And these tools you want to make super hard on a surface level. So you want the surface of these tools to become very abrasion resistant. They should not wear, they should not break, they should be super hard because they are used, for example, in cutting. This can be the head of a tunnel maker. It could be the head of a drill to make oil rigs, for example, and so on. So you can imagine lots of applications where you need a super hard coating, and the way you make this coating in that case is that you blow all the components of the coating as chemical vapors, and that vapor is then going to deposit on the surface of these little things that are the tools. And what you don't want is that you have a surface that looks like a wave, that's totally wiggly, because if you have a wiggly surface, well, obviously it's going to create asperities and sharp changes in shape, and that thing is not at all what you like, because if you have that, then you will create concentrations in stress when you use the tool, which goes opposite to what you are interested in, which is to create a tool which is resistant and able to sustain large loads without breaking and without wearing off. So that's what you're interested in here. You really want to have a very flat surface such that when you use the tool, you do not create large stresses. You can imagine if you have a wavy surface, you try to press, the stresses will be much higher than if you have a flat surface. Upon a flat surface, well, the stresses will be equally distributed and you won't have localization of stresses. So that's the key question. How do I make a surface which is flat enough? And why is that useful? Okay, you have applications here on the left. You can very easily see it. It's very useful for electronics, for solar panels. It's used to make a lot of tools where you need to have some very thin surface that is controlled in terms of thickness. And the problem, obviously, maybe obviously, I don't know, is that if you blow whatever chemical vapor from the bottom and you move up the cylinder, you can imagine that the conditions in terms of pressure, velocity, and concentration of these species is going to vary along the height. So it may be that at the bottom you have a higher concentration, at the top you have a lower concentration because there was already deposition. So it's a quite complex process because in order to really understand what's going on in there, one way is to simulate the flow, the chemical reactions that are taking place, because lots of chemical reactions are taking place. The deposition process can be also simulated. And at the end, you have some model version of this. So what you are using here are the conservation laws that we were talking about in the more theoretical part of the course, where you are saying, okay, what is being conserved? Well, I have chemicals that come in. Whatever comes in has to either stay there and transform into something else or leave. So either whatever comes from the bottom here is going to be deposited along the height, along these cylinders, these little plates. So it's going to be deposited. And then something comes out, what was not deposited, or everything is going to be deposited inside and there is no remnant at the top, or what comes out at the top is the product of the chemical reactions, because if you, for example, put some carbon with oxygen, you put the carbon with oxygen, you get CO2. So CO2 is the product, carbon and oxygen were what you put in. So at the top, you have no carbon and no oxygen left, but you have CO2, for instance. That would be an example. So now, what is the question here? Well, now we have these chemical reactions. We have these pressure, velocity equations. We have conservation of mass and species, and all these conservation equations, which we learned how to write. These equations are going to help us write what we had on the left-hand side of the slides I showed in the previous part of the presentation. So the hypothesis-based models. So that thing that you write down using equations, that is what you're going to have here. And well, okay, that's great. The thing is, of course, we're making huge assumptions. So you can imagine that there is a flow in there, which you can wonder whether it's a turbulent flow or a laminar flow, because, and in order to figure that out, you can compute Reynolds number, which is one of the non-dimensional numbers we talked about in the beginning as well. If you remember, when we tried to non-dimensionalize everything, here, if you use that, you see that the flow is going to be laminar because the distances between things, so the length scale is quite small, and that is going to lead the Reynolds number to stay relatively contained. So we're not blowing things at 200 kilometers per hour at huge concentrations over very large distances. We have a very small distance between these different inserts, and this is the way it looks. So for example, all these blue dots here, I hope they are blue because I'm colorblind, but if they are not blue but pink or violet or mauve or whatever, you'll bear with me with that. But all these little colorful things, dots, they correspond to each of the tools that you see on the right? So that means there are lots of these things. And it could be that maybe on the outer sides, because of the boundary effects, the thickness will be different than in the inner circle, because in the inner circle, you're going to be closer to the source, and it could be that the thickness is more. And so all these questions are very complicated, very complex. And therefore, if we start embarking on modeling this, which we did, we don't go very far, because it's super complex to be able to know what parameters are important, which ones are not important, which factors are important. Should we take the pressure into account, the velocity, the conservation of mass? Should we forget this species, forget that species, add this equation, remove that equation, chemical reaction equation? Do we actually understand the chemical reactions properly? Maybe we forget something because we don't realize that under these conditions of temperature, pressure, velocity, some chemical reactions are more likely than others to happen. This is also what happens in cells. In cells, it's the same problem. When you look at the genome, you see what the blueprint actually is, but it doesn't tell you what actually is going to happen. This is what you see when you look at the proteins in the cell. This is what tells you what actually happens between the genetic information, the replication, which is the RNA, which you all know because of COVID PCR tests. They were measuring what is the RNA in your cell that actually looks like the virus. And that means that the virus is trying to replicate, right? Because if the RNA is there, it's trying to make the proteins that it needs. And so that guy is going to be there. If you want to measure how much of something there is in a cell, you just look at the RNA and it is going to tell you what is the probability that you will get these proteins, but it doesn't tell you for sure that the proteins will be there. And it could be that some proteins are in higher proportion than other proteins. Here is exactly the same. You're in the case where you have chemical reactions. They will produce outputs, so results, let's say, products. And these products, they may be in higher or lower quantity. That you don't know in advance. So this is a tricky problem. And so your goal, which is written here, is that you want to predict the thickness of the coating. That's what we explained clearly. Then you don't know what parameters matter, so you want to figure that out. What parameters means how much pressure you put, what velocity, what are the initial conditions, what are the boundary conditions. You would like to decrease quality control costs, because every time you make a mistake here, you can maybe throw the tool away. So your outcome is actually in the garbage, which is very bad for a company. You don't want that. And you want to optimize the reactor setup and the sensor positions in order to make sure that you minimize the error on the coating thickness prediction. And finally, this is what I was explaining about this super cool idea of large language models for people to express in their own need, in their own way, in their own words, the way that they perform an actual experiment. What is the name of this tool in the catalog? How did they position it in the tray? Did they put it at the top, bottom, left, right, whatever? All that can be said in words and can be used directly as words in order to teach the expert system what to do. And this is what we are going to talk about. So as you can see, another question that's very important that I just talked about is how to optimize the reactor setup. That means, how do I put these trays on top of each other, right? In which order do I put them? You see all these little holes here, they are not random. They are chosen in order to facilitate the flux of the chemicals in the reactor. And then that tells you where to put the sensors, because you cannot put sensors everywhere, it's too expensive. But you can put them somewhere, and where should you put them such that you will maximize the amount of information that you draw from these sensors. And these are questions that are super hard to answer, but also extremely useful for companies. And this, I'm talking about one company here, but other, tire manufacturing companies we worked with are doing exactly the same thing. They try to put the sensors in the right place and make decisions on the fly as to where to, how to inject the molten natural rubber in the die such that you get a certain quality at the surface level. And all of that is done using all sorts of thermal cameras and standard optical cameras, microscopes, and so on, that you can use in real time to do that. For high furnaces, the way people make steel, same thing. You have sensors everywhere. The feeding rate needs to be controlled. How much coal do you put there? How much iron? And at which level of the high furnace? All of these questions, they are industrial questions where people use a lot of sensors, data, and so on. In ecology, that's the same thing. You put trackers on animals. You'd like to know if these trackers are actually doing a good job, if they are insufficient in numbers. Should you put more? Should they be able to speak at a longer radius, and so on and so forth. So this is always a very important question to ask, where to put the sensors. And this is called, in the jargon, experimental optimization or experimental design. So you're trying to design the experiment that will optimize your ability to identify which parameters actually matter and to identify the value of these parameters, which allows you to fit the data that you see. And the difference between what's going on today in this world and what went on maybe 50 years ago is that 50 years ago, we could already compute stuff. So we could perform numerical simulations of a plane crashing in a nuclear reactor. We could perform structural analysis. We could perform maybe a dynamic analysis of a building to know how it reacts under an earthquake. But what we couldn't do is take into account the data as the data was being recorded. So we were able to perform a simulation of an aircraft durability. We could say between flight 1 and 10,000, the crack will grow by 1 centimeter, and therefore we will need to have an inspection of that aircraft before flight 5,000 because we expect that the crack should not grow more than 20 millimeters, than 2 millimeters, otherwise there will be failure in the aircraft. So this is a pre-calculation. We measure the crack, we let the thing take off and land 5,000 times, then we measure the crack again, and we say, our model was not very right because I predicted a growth of 1 millimeter and it actually grew by 2, which is catastrophic. You never want that. You always want to be conservative in any industry, especially the aerospace, which is obviously safety driven. And so what do? Then you upgrade your model, but you upgrade it once the aircraft has already landed. Now what you're able to do, exactly as in this case here, is that you're able to put sensors on the thing as it lives its own industrial life. And in parallel, your model is living its own computational life, and it's exchanging data much more frequently, maybe in real time, between the real structure, the real device, the real asset, and the computation, the model. And that means that your model is not wrong for so long anymore. It can learn from what you measure. And when I say it can, I'm lying a bit because in many cases, it's still an open question. How do you do that? Right? Because this is very difficult to do. Why is it difficult? Because the data comes in huge streams that is usually uncategorized, is messy, it's ugly, it's low quality, it's not even recorded properly. People forget to record it, especially in industry where they are not used to that because they didn't think of the idea of recording all of that. So they have the data, but they don't know what for. So it's just raw data. It's not organized. So not disorganized data is as good as no data because you can't do anything with it. You just have a bunch of numbers. You don't know what they correspond to. That happens a lot. Especially in big industries like the steel industry, people have huge amounts of data, but you don't know exactly what it represents. All right, so that's what we're trying to do. And that's super exciting, by the way. And that has a keyword behind it, which is called digital twin. You probably heard about digital twins. You can make digital twins of traffic jams, traffic in cities, traffic in Luxembourg, which is a very particularly nice place to do digital twins. But the most obvious digital twin you know about is climate prediction and weather forecast, because in weather forecasting, the problem is a bit similar to what you see here in this chemical vapor deposition device. You have super nonlinear equations, they are Navier-Stokes in that case, and these super highly nonlinear equations, as soon as you change anything in the boundary conditions, initial conditions, or whatever else, everything changes. So you cannot just pre-compute and hope it works. It just fails miserably because of the high nonlinearity of the problem. This is, this is known as the butterfly effect. If a butterfly flaps its wings in Tokyo, then you have a tsunami in New York, or vice versa. So this is something that you need to think about. So that is here a little bit how the reactor looks like in 2 dimensions to start with. And this is the CFD, meaning computational fluid dynamics. And these here are the equations. So you recognize the equations that we looked at, because that is nothing more than the conservation of mass, because rho is the density. So you can recognize that. So you see what we did until now should have a little bit of a positive effect, because you can now see that. And you see this is a time-dependent equation. You see that here you have divergence, and you see that you have here 0. So there is no flux. You have only this divergence, which is the change in rho and times u. And the change in rho times u is equal, essentially, the spatial change is equal to the change over time. So the fact that rho changes is only due to the fact that it changes over time, over space. So space change comes from time change. And this is what we talked about. The second equation is, strictly speaking, well, probably exactly the same, I would say, except that now you have something that comes from the temperature, which is written on the right-hand side, and you have something that comes from the species. So don't worry if you don't understand all these equations, that's absolutely fine. But at least the nature of these equations, you should have an idea what they mean now, because it looks pretty much like what we've talked about. And the last one is essentially Navier-Stokes, which is the equation that governs the flow of fluids and gas and water and whatever else. And so you have here the reactions, which are volumetric reactions and surface reactions. This is what happens at the surface. And this is what leads to the creation of the coating. Okay, so now if you look at the right-hand side, well, what you see is that you're able to compute some stuff, whatever that means to you. For now, probably nothing, but you're able to compute something. And you see these nice little colors. Now the problem is that each of these simulations is going to take something like a week. So if you want to, just to give you an idea, if you want to compute all of that stuff over the time that the chemical reactor works, you're not able at all to compute that in real time. So meaning the time it takes to compute is much larger than the actual time that elapses during the use of this chemical reactor. So what it means effectively is that you're not able to build this so-called digital twin, because the computational model lags behind the real case. So you could not start actuating the reactor by a control loop that would change the feed rate, the amount of chemicals being fed in there, what the pressure velocity is. You could not do that in real time because your computation is much too slow. And that is why you usually want to develop these surrogate models. So these surrogate models are surrogate, like surrogate mother is a mother which replaces, let's say, the real mother. You can't replace a real mother, but at least now with in vitro fertilization, you could take a fetus and put it in the womb of a mother who is not the natural mother of the kid, but serves as the replacement. So this is the way why I guess the word surrogate was used. I suppose surrogate simply means to replace. So you replace the model by another model. And here it turns out that this model that you use as replacement is very much faster. So your goal is very simple to understand. You have here a super complex, I'm saying 1 week, I'm probably wrong, maybe it's 1 day, you know, because in 2D, I guess it doesn't take 1 week. I mean, in 3D, the time to calculate that, I would estimate easily to be a week with current capabilities. But even 1 day, let's say it's 1 day, and you want to be able to control the system in real time. If you want to control that in real time, you need probably to compute that in 1 second. And so you need to move from 1 day to 1 second. That's a lot of reduction. And this is the whole problem of what's called surrogate modeling. And this is what this part of the course is going to be about. And I'm going to show you a few ways that you can do that. by going slowly and surely so that you are not lost. Now, I'm starting with these motivation example because I find it extremely telling, but we could have worked with almost any other example from real life, and I chose that one because I guess it's very easy to understand, and it's also multidisciplinary, and it also contains these chemical reactions and conservation laws that we talked about so many times. What you see on the left is that stack of 3 trays on which you put these little tools that I'm showing on the screen. Now, what you see around that stacked set of inserts and disks in the chemical reactor are the parameters that we considered. So this is a very, very, very long-standing project. We started more than 5 years ago, and the results that I'm showing are the results of 2 PhD students plus 1 postdoctoral fellow working for over 5 years. So this is 5 plus 4, 9 plus 4, 13, approximately 13 man-years behind this work. So if you don't understand everything, that's not surprising, because there is a lot of people and a lot of brain power behind that, which explains quite a lot if you're a little lost. But I think I'm going to be able to make it clear. So all around here, you have these parameters. These parameters are sometimes quantitative, meaning numerical, and sometimes they are categorical. So the numerical ones are of that color, and they are the most numerous. You can see them here. For example, a numerical parameter would be number of inserts on disks. That means number of these little things that are here. How many do you have? The insert surface area, standard deviation. So what is the surface area of that insert? Insert is this, right? These little tools here, they are called inserts. What's the standard deviation of that stuff? What is the surface area? What is the model of what is below the disk and above the disk? What type of model is that? What is the disk model? That's a number. What is the insert surface area? What is the surface area of that guy here, for example? And then, okay, recipe version, meaning what do you put in the chemical reactor? What's the soup that you have? Then you have this categorical features or variable. When people talk about features in machine learning and AI, they mean parameters. They just call it features because why not? Because parameters, I guess, is not fancy enough, so people had to come up with a new word and they called it features. Personally, I like to think of that as parameters because this is something you can change. A feature sounds a bit like something you cannot change. So I like very much better the word parameter, but fine. Then you have the insert model. So what does it mean, model? So model is going to be, is it this little shape here that looks like a diamond? Is it that one that looks like a more cube? Or is it that one that looks like a prism? So extruded triangle. So what is the model? And what is the model above that one? And what is the model below? So that model thing is not going to be just a number, it's going to be what is the shape? So it's going to be a shape of these inserts. It's going to be non-uniform rational B-splines. It's going to be splines. It's going to be circles or discs or cylinders or whatever. You cannot just say, with a number, you can't do that. So we're going to say, you can imagine that the designer will say, okay, I built such a shape using such and such tool, and I used additive geometry or subtractive geometry or Boolean, geometrical models and so on, and I did this and that and this is the input file, and there you go. That's the categorical features. What is the category in which that fits? So certain can be directly written by numbers, as you can see, and others cannot easily be written as numbers. You need to work more. So as long as things are numerical, what we did is we used an approach called XGBoost, which is very well known, which I'm not going to talk about in any detail, because this is not the point here. There are courses on machine learning that would do that much better. I'm going to tell you what we do with it, not what it does. And then that is going to output the coating thickness. And that's it. So you see, then what you do is you say, okay, let's do a prediction. This is the normalized coating thickness that I'm showing here on the y-axis, top right figure, and the actual thickness normalized. And then you see if you are actually able to predict the actual thickness using your prediction. And similarly here, you can check if the actual thickness is working well or not in different cases. All right, so that's what you do. And then what do you do with the categorical variables? Well, you transform them into numerical. And variables, you doing what? Using these large language models or natural language processing. All these insert models, they come from a catalog where they read like ABC 3264-3. That one as well, you know, whatever number, hexadecimal number, or whatever code that is being used, it's in a catalog, and it describes, although not computationally or numerically, but it describes what's going on. So then that you can transform the text that's written here, this little note, and you can transform that into some neural network. So you feed it to a language model, and that language model can be specific to the application that you're looking at. It need not be a language model that is a generic one like ChatGPT. You can have your own proprietary language model, which I would recommend, because this way not everybody can read it and get your ideas and play with them without you being the wiser. And then you make a matrix out of that. And that is now the input features of the XGBoost algorithm, which will give you a predicted coating thickness or whatever it is that you're interested in general. So this is what that word means, enriched with embeddings. So embeddings means you take these categorical features in natural language, transform them through a neural network into numerical values, and those become the new parameters. And that is what is called an embedding. Embedding in, let's say, computer science, machine learning, AI, just means that you transform that into a feature. So into a parameter. Feature space is also what people talk about. And here, what you see is the predicted observations versus the actual observations. You would like this line to be, you know, exactly y equals x, essentially the first bisector. And what you see is that, okay, well, it's not perfect, but if you look in detail at the training set and the test set, because obviously when you train a machine learning model, you train it on a part of the data and you test it or verify it or validate it on the rest. This is called cross-validation. You cannot, obviously, test your machine learning model on the same data that you trained it on, because that would not be a test, it would be a foolish reproduction of what you already did. So what you can do though is, okay, just give me a second. Give me a second, please. Right, sorry about that. So we were saying that, yes, you compare to, so you have the test space and you have the learning space. And of course, they are not the same. And as I was trying to show with my hands a bit earlier, you are able to compare two setups, let's say, right? So if you look here, you basically have a matrix, and this matrix is going to help you compare two different vectors if they are close to each other or if they are far from each other. And that's going to be able to compare in a quantitative way what otherwise is written in a book or written in a catalog. You have, model 123 XB5-3. That model, how do you compare this model to 123 SB6-8? You don't know a priori, but now you have a quantitative way of comparing these two situations, which are for these two little different inserts, because now each corresponds to a vector in that feature space. And all you do is you compare the signs, the direction cosines, so you compute some sort of dot product or normalized by the norms, and that gives you how similar these two vectors are with each other. And from there, you find similarities, and you can put in some sort of hyperspace, right, that you have here. In this hyperspace, you can put these little guys, like circular around a triangle, triangular around it, whatever, rectangle, square, 35 degree rhombus, 80 degree rhombus, and so on. You can put all of that in a space, and you can compare directly, precisely what's going on. And I think that with a bit of creativity, you guys could be able to figure out whether it is for your research project that you are working on, for your graduate degree, for your PhD or your postdoc, or maybe you want to do that for your master's even. You could think of cases where you would like to have these categorical variables and you would like to embed all of that in words that would then be rewritten in terms of quantitative data, which would be numbers. And I think you can think about that for your own problem and project, and maybe that will be useful. And if it is useful to you, then by all means, we can get in touch together, and I can put you in touch with Jeremy, who did everything in that work, so that you can then start thinking whether you would like to go in that direction, because we'll be working a lot more in this direction in the next years. And so now the question also, obviously, once you have all these wonderfully useful data, you'd like to figure out what are the parameters that are really useful. So that's an important question, which also asks itself in your case, for whatever problem you are dealing with. This is a question that you will need to figure out. So you will have some data, which is production data, and you will have an idea of what parameters are useful. Because if you remember in the previous set of parameters, you can count here 1, 2, 3, 4, 5, 6, 7, whatever, 12 also parameters. And 12 parameters is a lot. Let's say that you need to vary each parameter, take 10 values of these parameters for each parameter. You have 12, that's 10 to the power 12 values, combinations that you need to look at. So 10 to the power 12 is much too many, even if you have a surrogate model for each simulation that is going to give you, in 1 second some results. You still have 10 to the power 12 simulations to make, which is 10 to the power 12 seconds, is still far too many. So you're not going to be able to optimize the system, right? In order to optimize the system, the best way that we know today is to do a two-step process. The first is a clustering algorithm, which allows you from the production data, which gets directly measured. This is not online, this is offline. That means that you do not do these measurements in real time. You perform these measurements once every day, for example, and you take measurements, or every month, every week, whatever. This is called offline. This is the production data. So this is offline, this is the production data, and this is the way that you can categorize the values and the parameters that are important or not important. So you have a lot of ways to do that using Shapley values and so on. This is something that comes from the field of uncertainty quantification. And the idea is to try to find first the clusters of runs such that you are able to figure out what differs between different paths. So you can use a lot of methods to do that. And then once you've done that, you can find the common characteristics of the production runs, which means what you measure, and then look at the impact of the process parameters on what is taking place here. Okay, so that was done by Jeremy, and he found out that using NLP allowed to really help with the Shapley values, which are the importance values. You see that you get certain features that were unimportant, so certain parameters on the left that were unimportant, but now that you use the natural language processing and all the data about the categorical variables or parameters, then suddenly you see that certain unimportant parameters became important, and that others that were more important became less important, like the last one, total area, for example. And so that gives you a lot of information that you can then use in order to optimize your process. So this is really the key points here. Okay, so now what are the parameters that matter? The way we do that is using the following approach, and this is done really all the time for a lot of processes. So first of all, you have inputs, which are the shape and the pressure, velocity, chemical composition of the vapor. Then you have this computational fluid dynamics model. This is what you use, Navier-Stokes, the equations I showed earlier, conservation equations, which we learned how to derive. Then from there, you have some outputs. And these outputs, they allow you to do dimensionality reduction. And this is what I will talk about in the next lectures, in particular, a bit later today. And then once you have this dimensionality reduction, you can do clustering of the results, which allow you to figure out what are the parameters that matter the most in terms of cluster. So you say, for example, that range of parameters leads to a cluster of solutions here, and another range of parameters leads to another cluster, and a third. And then for each cluster, you will do a sensitivity analysis independently, and that will give you the most influential inputs. So what is a sensitivity analysis in practice? The problem with that is that it requires a huge number of runs, because sensitivity means if I change the parameter a bit, how does it change the simulation result? That is the question. And then in order to do that, well, you can do it either a priori, which means that you compute the derivative of the quantity you're interested in with respect to the parameter. So that's what you can do. Or you can do it a posteriori once you have the data, and this data is going to tell you what, where you have higher gradients and where you have lower gradients with respect to the parameter. And computing these gradients allows you to compute the sensitivity of the output, which is the quantity of interest, with respect to the parameters that you're interested in. And this is always very telling and very useful to do. But to do that, you cannot do it without a surrogate model, because to perform a sensitivity analysis, you need to solve a lot of problems. Because think about that this way, your sensitivity analysis is done by having a parameter distribution. So you have a parameter distribution, but distribution means statistical distribution. So it means that you have this bell-shaped curve, for instance, and you need to sample the curve. You cannot just take the average and mean and standard deviation. You need to average the curve somehow. You need to sample it. So to sample it, it means that you cannot just do one run, but you need to sample the distribution. So take a few values that are descriptive of the distribution, and then to solve the problem for all of those values and take the average, standard deviation, and all other statistical moments you may be interested in. That means that you cannot do one run, but thousands of runs. It is called Monte Carlo analysis, that you probably heard of. And this Monte Carlo so-called analysis is nothing else but doing averaging. So you take some darts, you throw it randomly at a target, and you measure what the number is. You throw it again, and you measure. Again, you measure. And the convergence rate of that is square root of the number of darts. So if you want to know the importance of a parameter, and you need to know the average, let's say, thickness of the coating in that case, you will need to run, let's say, 1,000 times the simulation for each parameter change. So now you have 10 to the power maybe 6 parameters. You're going to have to run this 10,006 times, because you know now that you have a reduced order model, it's not 10 to the power 12, but maybe you reduce that to 10 power 6, but then you need to run that 10,000 times. So it's still a lot of runs, actually, too many runs in that case, right? So you need then to move forward with that. And that is why you need to have a surrogate model, because the surrogate model accelerates everything. And without that, you would be totally incapable of solving this problem. Okay, so that's basically that. And then the next step, which is much harder, is not to transfer the uncertainty forward. Forward means between the input and the output, which is the coating thickness. No, that is the forward uncertainty quantification that I just explained. But what you actually want is to start from the uncertain statistical distribution of the coating thickness, quantity of interest, and then to back calculate what were the inputs that caused this distribution. So this is called an inverse problem, because you look at the solution and you want to find the problem. This is very difficult because it's ill-posed. You normally cannot solve that in a unique way. Almost never actually. You always have to make some assumptions that are called regularization. So this regularization can be done, and is typically done using Bayesian inference, meaning that you add prior knowledge in order to decide what is the possible cause of what you see. And this is always the same in Bayesian inference. You see something, and you are looking for the probability of what you see to be true. That is something very counterintuitive that I already explained, but I'm going to explain again now. When you do this inference, you look at something. This is the evidence. But then you have in your mind or in your model a prior knowledge. And that prior knowledge is or not, or more or less, compatible with what you see. For instance, if you start seeing cats flying, you're going to think that something is wrong. You're going to be surprised, right? So same thing with, there is experiments that were made for psychologists, for kids, babies, to figure out whether they understand that things are, whether they can count without realizing. So I could show you these experiments. They are very fun. They have blue balls and yellow balls. in a bag and there is a majority of yellow balls, and they then hide all the balls inside the bag and they take one out, and the kid actually knows at 18 months that if there is a majority of yellow balls compared to the blue balls, if you take out a yellow ball, they will not be surprised, meaning they will not stare at you or open wide their eyes. But if you now take out a blue ball, which is much less likely because there is a majority of yellow balls in that bag, then they will look at you like this, meaning that they show surprise. And that is already the case at 18 months. So it means that somehow there is already numeracy embedded in the brain at that age, although of course they cannot count, they can see from a global picture what is the likelihood of having a yellow as opposed to a blue. So in that case, their prior knowledge, which is there is a lot of yellow, not much blue, is challenged by what happens. And this is what happens exactly in Bayesian inference. In Bayesian inference, you're going to observe a coating thickness. That is what you observe. And you'd like to explain it by your prior knowledge. And in that case, the prior knowledge is a parameter distribution of, let's say, parameter 1. And could be concentration of one chemical, like, I don't know, phosphorus, just to say some random thing. So that concentration is given in terms of a probability distribution, maybe Gaussian, or maybe log normal, whatever. And that probability distribution is supposed to explain what you see. But it could be that what you see surprises you relative to what you know of the phosphorus distribution in that input melt that you have in the chemical vapor deposition process. So that's what's called in inverse uncertainty quantification. And this is something extremely difficult that is used everywhere. It's used in the oil industry, in geophysics, to try to figure out what you don't see from what you see. You see the physical surface of the Earth and you want to figure out what's underneath. It's used in MRI. When you do an MRI, you actually look at spins. And so from the spins that you measure, how they come back, or from the water diffusion, if it's diffusion tensor imaging, then you see something else, you know? And that from what you see is you calculate back the properties that you're interested in. So this is a very, very useful thing to understand. And of course, the future looks like that. You know, the lab person or the engineer or the technician is going to ask, I want to know the coating thickness if I set up a reactor with 500 square inches of type 1, diameter 5 centimeter at height 2. And boom, the advisor will tell this person that there is a probability of whatever to get a coating thickness of 5 centimeter with a variability of 0.2 centimeters. So you see, if we manage to do that, it's going to be a super nice way forward. And all right, so now I'm not going to tell you about the astrocytes right now, because I would like to be able to tell you a little bit about the theory before we end around, I would say, 11, if that's okay with you, unless you would like to keep going further. And unless you have comments, if you have comments, you can maybe make them now.